Hello everyone, a very good afternoon to you all. I am here, the chemistry educator of SPSVERSITY, with the new topic of grade 12 in the second semester, or you mean to say the second part, which is aldehydes, ketones, and the carboxylic acids. So freshen up, guys. We are going to listen a really great, wonderful session. Here we go. If you really like our videos, press the subscribe and the like button, and then we move ahead with this topic, that's aldehydes and ketone and the carboxylic acids. We are going to take it in two different parts. One is the aldehyde and ketone, and the other one is the carboxylic acids. So the common thing which is there in aldehydes, ketones, and the carboxylic acid is the C double bond O group, which is called as the carbonyl group. Okay, then the carbonyl carbon is always sp2 hybridized because the carbon is attached to a double bonded oxygen, so it is sp2 hybridized. And now, how the structure is for this? Since the carbon is sp2 hybridized, it is in the trigonal planar shape, and you have one unhybridized p orbital that is going to overlap to form a pi bond. So this is the CO single bond, which is a sigma bond, and then these are the unhybridized orbitals, which contains one electron here that is going to overlap with the pi unhybridized orbital of oxygen to give a pi bond. This is a if the sigma bond is axial head-on overlapping, this is a sideways overlapping, so this leads to the pi bond, and always in the reaction it is a pi bond which is going to be broken and not the sigma bond. And this is a new orbital, hybrid orbital formed after this is a hybridization formed, and then this is the new orbital, like after overlapping. So after this, what we have is C double bond O, where the oxygen is more electronegative compared to oxygen because oxygen is more electronegative compared to carbon. This is why this is called as a polar bond. What exactly is a polar bond? As all you know, polar bond is a bond formed between two different atoms which differ in their electronegativities. So because of which one develops a partial positive charge, the other one develops a partial negative charge. And here the carbon, if you compare the electronegativities or negativities of carbon and oxygen, oxygen is more electronegative compared to carbon. This is less electronegative. So the oxygen is going to drag the pair of electron towards itself by developing a negative charge, whereas the carbon develops a positive charge on it. So this bond is considered as highly polar. So whenever the reaction happens, the bond gets shifted toward the oxygen atom. And when in case of aldehydes, if you say the aldehyde, it will be RCHO. This is the alkyl group, and then you always have the CHO group. If it is a ketone, then it's RCOR. You have a two alkyl group on either side of the carbonyl group. If it is a carboxylic acid, then RCOOH. One side you have an alkyl group and the other side you have OH group. And if it is an ester, then it is RCOOR. These are different carbonyl groups which you come across in your grade 12. And also whenever you say the ketones, there will be symmetric ketones as well as asymmetric ketones. If both the alkyl groups on either sides of the carbonyl group are same, then it will result in the formation of symmetric ketone. If they are different, then it will result in the formation of asymmetric or unsymmetrical ketone. So how do you name it? Always this aldehyde comes at the end. For example, if you have CH3, CH2, and CHO, then you have to start the numbering from this side, which contains the functional group, that's CHO. So 1, 2, 3, there are 3 carbon atoms, because of which this is called as prop. The root word is prop. The type of bonding is ane. At the first position you have aldehyde. Aldehydes end with the letter Al. That's the suffix given to the aldehydes. But unlike aldehydes, ketone always come in the middle. If you remember that, CH3, C, CH3, and you have a double bonded O here, and this is CH2. In that case, you have to name in such a way that since the carbonyl group is going to come in the middle, you have to give a smallest number to this. So if you go by this way, this gets a 2 number. So there are 4 carbon atoms, so it should be but. Type of bonding is ane, and at the second position you have one. So it is called as butanone, 2-butanone or butane 2-one. This is about the nomenclature, and if you have um, benzene ring with the aldehyde group, then it is called as benzaldehyde. The same way you are going to name different aldehyde and ketones in a different way. And about carboxylic acids and the esters we are going to discuss in the next sessions. So how do you prepare them? How the methods of preparation of aldehyde and ketone is done? The first method of preparation is by the oxidation of alcohols. Alcohols are ROH groups, and then the dichromate, which is a good oxidizing agent. This can oxidize. Say if you take the aldehyde as RCHHOH, if this is the alcohol, and if you are going to oxidize it, then the hydrogens will be removed. How do you define the oxidation? As the removal of hydrogen as well as the addition of oxygen is called as oxidation in the presence of acidic potassium dichromate, which acts as a good oxidizing agent. What is going to happen is RCHO, if this is a structure, the removal of the hydrogens takes place over here, resulting in the formation of an aldehyde. Here you get a double bond. So if you start with the primary alcohols, that is alcohol OH attached to a carbon containing 2 hydrogen atoms and 1 alkyl group, then it is called as primary alcohol. And then if this compound, say RCOH HH, then these two will, say this will go, resulting in the formation, say these two will go, resulting in the formation of a double bond here that leads to the formation of RC double bond H. This is aldehyde. And if you start with R secondary alcohol, RHOH, then what do you expect? This hydrogen and this hydrogen will go, resulting in the formation of a double bond over here that leads to the formation of RCR double bond O, which is nothing but a ketone. So always the primary alcohols lead to the formation of aldehyde, and the secondary alcohols on treatment with the good oxidizing agent acidified potassium dichromate to give the ketone. So if you take the aldehyde, these are quite susceptible. That means if you on further oxidation, they may get oxidized to corresponding carboxylic acids. Okay, so the oxidation of primary alcohols is made at a temperature above the boiling point of the aldehyde. So because of which aldehydes are vaporized and they are not oxidized. That is what is meant by the susceptible. But the major thing what you have to remember is aldehydes are obtained from the primary alcohols, and the ketones are obtained from the secondary alcohols by treating them or by oxidizing them with strongest oxidizing agents like acidified potassium dichromate. Then dehydrogenation of alcohol. What do you mean by dehydrogenation? The removal of hydrogen from the alcohol. Removal of hydrogen molecule from the alcohol that results in the formation of aldehyde or the ketone. So how is this reaction going to be done? So you take the primary alcohol. I'll expand the structure over here. An O and a H, copper at 300 degrees Celsius. Then what is going to happen? Say from here one H will go, from here one H will go. So this results in the formation of dehydrogenation, removal of hydrogen, resulting in the formation of CH3, C and a H down and a double bonded O. Since the hydrogens are being removed from here, you get a double bond in between. This results in the formation of an aldehyde. Again, the primary alcohol, if you see, just like the previous reaction, primary alcohols resulted in the formation of aldehyde. If you take the secondary alcohol, that's CH3, CH3, OH and a H. And if you do the same reaction, when it is heated with copper at 300 degrees Celsius, one hydrogen from here will go, one hydrogen from here will go. Because two hydrogens are being removed by the neighboring the atoms, you will get a double bond in between them. That results in the formation of CH3, CH3, C double bond O. This results in the formation of a ketone. So the primary alcohol is going to give you an aldehyde, secondary alcohol is going to give you a ketone. If you take the tertiary alcohol, so there is hydrogen can be removed from here, but there is no hydrogen attached to this carbon. So what is going to happen? You can't remove this way. So if you take this one, CH3, C, CH3 and C with the three hydrogens over here and OH, then if you heat it in the presence of copper at 300 degrees Celsius, then a water molecule will be gone because the water molecule is gone from the neighboring atoms. That's OH and a H. You get a double bond over here. That results in the formation of CH3, C, CH3, double bond CH2. This results in the formation of an alkene. So the primary alcohols on dehydrogenation in the presence of copper at a higher temperature will result in the formation of aldehyde, and the secondary alcohols will, under the same condition, they lead to the formation of ketone. And the tertiary alcohols, if they are treated with the same reagent, that's a copper at 300 degrees Celsius, then you don't have any hydrogens attached to OH, which is attached to a carbon atom, because of which a water molecule is gone, and this reaction is important. A water molecule is eliminated, because of which you get a ketone. Okay, then what are geminal dihalides? What are geminal dihalides? If the halogens there are two halogens attached to a single carbon atom at the end, then it's called as terminal dihalide. So if you hydrolyze them in the presence of, say, aqueous KOH, potassium hydroxide, then these two chlorine atoms get replaced by OH from the KOH. So as a result, CH3, CH double OH, this the two OH groups attached to a same carbon, they are pretty unstable, because of which water molecule gets eliminated like this. You get CH3CH and double bonded O, that is nothing but the aldehyde. So from the terminal geminal dihalide, you are going to get the unstable dihydroxy compound, which on T mole of water molecule is going to give you an aldehyde. So let me check how many of you are watching the videos. If you like the videos, please click the like and subscribe button. And yeah, here we go. And if you have suggestions, please, you can put your suggestions in the comment box, which we can see it later. And yeah, and we can improvise ourselves. Okay, the next reaction, there is an example. And also, if you take the geminal dihalide, but it is not terminal, it is not at the end. If you take it in between, for example, two chlorines are attached to this one. So because of which, what is that you are going to get now? So here, if you are going to treat them with KOH, one OH will be removed from here. These chlorine atoms are going to be substituted by OH2 OH groups, and then a water molecule from here will go, results in the formation of a double bond between these two, that results in the formation of a ketone. So always it's just like if you consider the previous two reactions, you can clearly see that the primary alcohols resulted in the formation of aldehyde, and the secondary alcohols resulted in the formation of ketones. And here, if the just like the primary alcohol, if the OH was at the end, as the same way, if the two Cls were at the end, you got the aldehyde, and if the two Cls were in the middle, then you got the ketone. By oxidation of diol. What do you mean by diol? Diol is a compound in which, in a particular organic compound, two OH groups will be there. Two alcohol groups, OH groups will be there. That's called as a diol. When per iodic acid, just like uh, when per iodic acid is that's HiO4 is treated with lead tetraacetate, that's lead and tetraacetate. The charge on the lead is 4 and this is the acetate ion. When you cross this, you are going to get CH3COO4 Pb. Vicinal diols get. What do you mean by vicinal diols? Vicinal diols, geminal dihalides are geminal in the sense two groups are attached to the same carbon. If it is vicinal, they are attached to the neighboring carbon atoms. Then they get oxidized in the presence of periodic acid, which is going to provide the oxygen. And then what is the reaction happening over here? So if you take the geminal dihalide where the OH groups are attached to the neighboring carbon atoms, and now this bond will break, say R, CH, OH, and this results in the formation of a bond breaking over here, and here you get a double bond R, C, O, and a double bond over here, and the same way R dash CH, a double bond O. You are going to get per iodic acid gets converted to iodic acid, just like nitric acid HNO3. Iodic acid is obtained along with RCHO and R-CHO. Hope you get it. If these two are hydrogens, which are attached to the carbon atom, then you are going to get the aldehydes. Instead, if they are the alkyl groups, if you see all of these are the alkyl group, and if you now treat this diol with this vicinal diol with the periodic acid, then you are going to get the iodic acid. And what is the main product? Just like the before reaction, the bond is going to break here. You get C double bond H and C double bond O and C double bond O here, resulting in the formation of a ketone. Hope it's clear to you. This is about the reaction of diols. That's the vicinal diols with the oxidizing agent, resulting in the formation of aldehydes and the ketones. So let's go for the next reaction by the ozonolysis of alkenes. This you have already studied in grade 11. Let me recall it once again. So if you take the alkene, say we are going to take some random alkene, say CH2, that's ethene, and you are going to treat it with ozone. Then what is that you are going to get? You get a ozonide. So one oxygen goes here, two oxygens go here. As a result, you get a ring-like structure, that's CH2. The bond between two CH2 groups will not be there, so they get occupied by the ozone molecule. That's O, CH2, and OO. This forms a ring-like structure, and then it is going to break in a symmetric fashion, like this will go, and this is the other part. Because of which, what is that you are going to get? On one side, when it is heated with zinc, water molecule has been lost and results in the formation of H2CO. That's nothing but H, C, H double bonded O. And you're going to get one more molecule of the same kind, HC double bond OH. That's got nothing but the aldehyde. Instead, CH2, if you take CH3 and a H, then what is that you are going to get? Always ozone gets added in between the double bond, because of which you are going to get CH3, C, O, one more H over here, CH2, OO, and this bond is going to break this way. As a result, what is that you are going to get? Here, that again the aldehyde HCHO, and here this CH3, then CHO. This is what you are going to get. Again, it has aldehyde. Hope it's clear now. If all the hydrogens over here are replaced, for example, CH3, C, CH3, and CH2. If this is the compound you are going to take, and if you are going to treat it with ozone, then you are going to get CH3, C, CH3. There will be two CH3 groups attached to it, and you get a ozonide ring over here, and then this is going to break this way. And now what is that you're going to get over here? This is CH3CO, nothing but the acetone which you use in nail polish removers along with aldehyde. So depending on what type of reagents or what type of groups you have on either side of the double bond, you're going to get the corresponding aldehyde or the ketones. This is by the ozonolysis of alkenes. How do you produce aldehydes and ketones? So let's move forward. From alkynes, that's by hydration. What do you mean by hydration? It's nothing but the addition of water. So if you take an alkyne, the CH triple bond CH, and when you treat it with a water molecule, then one of the hydrogen gets added over here and the other OH gets added here. As a result, you are going to get CH and triple bond CH. If it was there, say you add OH to one and the hydrogen to the other, so you get CH2 here and a double bond and a CH and OH. This is nothing but double bond is ene and this is ol, so this forms the enol tautomerism, so it is very unstable, so the shifting will take place, because of which this gets converted to the hydride shift is going to happen, because of which this bond shifts over here, and CH2 with one hydrogen is going to become CH3 and C and the H, and you have a double bond between these two, and this results in the formation of the acetaldehyde. Then we have the hydroboration. The hydroboration happens in the presence of diborane or boron trihydride, or this is going to happen in the presence of peroxide. So this results in the formation. This mechanism proceeds through the anti-Markovnikov conversion. Okay, that if you take the prime one alkyne, that's going to give you the aldehyde. If you take the rest of the alkyne, that's going to give you the ketone after the hydroboration reactions. And then by the hydrolysis of the carbonyl derivatives. So if you have the carbonyl derivatives, what do you mean by the carbonyl derivatives? If you have CO, this is the carbonyl group. If it is H, this is aldehyde. If this two groups are RR, then it is ketone. And if it is OH and the R, then it is carboxylic acid. Instead of C double bond ON, OH, this is called as oxime. So it's clear, I guess, if the aldehyde, that's RC double bond OH, if this double bond O is replaced by NOH, that's going to give you RC double bond NOH. I'm sorry. If this double bonded O gets replaced by NOH, so what's that you're going to get? This will be NOH. And this is H. This is called as aldoxime. If this particular H is also replaced by one more alkyl group, that's R. If this is replaced by R, then it is called as ketoxime. So I think you know by now what is aldoxime and what is ketoxime. Yeah, we'll move forward with this one now. So aldoximes are RCH double bond NOH. If you hydrolyze this, acid hydrolyze this, then what is that you're going to get? Say I'm treating with it with water molecule. Then these compounds will go together. RCHO, the same thing over here. RRC double bond O, and you get N2 hydrogens with OH. NH2OH is nothing but hydroxyl amine. NH2 is amine and OH is hydroxyl group. So it results in the formation of hydroxyl amine. And if you again treat the ketoxime with, if you are going to hydrolyze, acid hydrolyze it, again the O will go with this carbon, resulting in the formation of a ketone, and you get NH2OH, nothing, this is nothing but hydroxyl amine. If you take the acetal, what is acetal? How do you get the acetal? Sorry, I'll write it down. I'll erase everything so that I can write it again. So your exams are nearing. You must be working hard. Yeah, here we go. So acetal, R C double bond OH. And if you're going to treat it with, say, ROH, then what is that you are going to expect? This will go and attack here. This will shift. As a result, you get RC H O, and this you have to treat it with one more molecule, because of which you are going to get O, R, and OR. I think it's clear to you. And this is called as acetal. If you hydrolyze it, what is that you are going to get? H2O bar H plus. Here you are going to get, or better, you do this way. You take an aldehyde, you treat it with 2 molecules of alcohol. This will be removed. As a result, what is that you are going to get? R, C, H, and you have here the double bond. One bonds with OR and the other bonds with OR. This is called as acetal. If there is only one OR, then it is called as hemiacetal. If there are 2 OR groups attached to this, then it is called as acetal. Now, when it is treated with when it is acid hydrolyzed, the reverse reaction is going to happen, resulting in the formation of an aldehyde and 2 molecules of ROH. The same way, how do you get the ketal then? R, C, R double bond O and HOR, HOR, because of which one water molecule will be eliminated, resulting in the formation of ketal. This is called as ketal. Again, this acid hydrolysis is going to give you the ketone back, resulting in the formation of 2 water molecules. Hope it is clear to you. This is how we prepare. This is how the preparation of aldehyde and ketone is done from the carbonyl derivatives. It is it can be oximes, or it can be acetal, or any other compounds. Yeah, we'll go ahead with the from the cyanides, how this proceeds, the reaction with the. So as of now, no one is watching. So when you watch this, you can please leave your feedbacks down in the comment section. Your feedback is really important for us, so that we can deliver better lectures in future. Yeah. From the Grignard reagent, we know what exactly Grignard reagent are. The as alkyl magnesium halides, RMgX is called as a Grignard reagent. So this carries a, being a metal, Mg carries a delta positive charge and this carries a delta negative charge. Now RCN, when they are treated with the Grignard reagents, I'll write the reaction over here. RMgX plus RCN. Now, this R being negative and this is positive, this goes and attacks here, so the bond shifts, because of which what is that you are going to get? R, C, it became the double bond, and you have attached MgX, which is a positive part because it gets a negative charge, and this R comes down over here. Then when you hydrolyze it, what is hydrolysis? You are going to treat it with this, so these will go together, resulting in the formation of ketone, and NMgX will so this will go as a ketone, and you get what are the other compounds which you are going to get. You have treated them with H plus, so you get the NH3 along with the formation of MgOHX. This is how the reaction is going to proceed. And even the RMgX can be treated with the ester also, that's RCOOR, or alkyl formate, that's the ester of formic acid. Then RMgX, R will go and attack over here. This bond will shift, to which MgX gets attached. So you get CH, R down, and then OR was already there in this compound, and O with MgX, which on hydrolysis, this is going to give you MgOHX. You're going to get MgOHX as a side product, and you have O, to which one hydrogen gets attached. This is called as hemiacetal, where you have R, OR, and OH. If this is also replaced by OR, the H over here, then it is called as acetal, which one water molecule gets eliminated from here, resulting in the formation of, say this goes, then R, C double bond OR. This results in the formation of an aldehyde. So if you take the alkyl formate, that's one side you have the hydrogen. If on either sides you have the alkyl group, then that results in the formation of a ketone. This is how it proceeds. This goes over here, this over here, this takes up this, because of which R, C, and R group over here, OR and OMGX, that on hydrolysis, that is going to give you RCOHOR. This is again a hemiacetal, which will give you a ketone later. By acid chlorides. Acid chlorides are the compounds where you have C double bond to the carbonyl group, you have the chlorine attached to that, that's acid chloride. When this is treated with RMgX, that's a alkyl magnesium halide, then what is going to happen? RCOCl plus RMgX. If this is a compound, then this R will go over here, okay, and this shifts here, and this goes and takes up here. Hope it's clear to you. Because of which R, C, O, and then you have R, Cl, MgX, which on hydrolysis, these will go together, resulting in the formation of MgXCl, and you get R, C, a double bond in between. That's nothing but a ketone. Then we have a famous reaction over here, which is called as Rosen-Munsell reduction, where the acid chloride, if you see this, the previous slide, acid chlorides are treated with alkyl magnesium halides. That's the Grignard reagent. You got the ketone. But here, when you take the acid chloride, that's RCOCl, when it is reduced in the presence of palladium over barium sulfate, then this won't be further reduced. Only, for example, RCOCl plus H2. You can add the H2. How do you add H2? This will go together. HCl is one of the product. You get RC double bond O and a H. This results in the formation of aldehyde. But the first aldehyde, which is formaldehyde, you need H over here, which cannot be prepared by this method. That is one of the drawbacks of this method. But rest of them, you can get them in the very good yield. And also, in case if you don't poison the palladium, if it is not poisoned with barium sulfate, then this will further reduce. This will undergo reduction to produce, that's RCHO. Then one hydrogen gets added here, the other hydrogen gets added here across the double bond, resulting in the formation of the alcohol. To avoid this conversion of alcohol, palladium is poisoned with barium sulfate. I hope it's very clear to you. Then we have the Stiffness reduction, where in case of Stiffness reduction, the alkyl cyanide is treated with the tin chloride and the HCl, which is a good reducing agent. So if it is RCN, I'm changing the ink so that you will be able to identify this is a different reaction. So R, C triple bond N, and then you have the reducing agent which adds the hydrogen over here, that result in the formation of an imine, R, C, H double bond NH, which on hydrolysis, acid hydrolysis, this will go, say you treat it with this like this, the CHO will come together, resulting in the formation of NH3. So you get the compound as RC double bond OH plus NH3 as one of the side product. So if you start with the ethane nitrile, then that results in the formation of propanol. Okay, I think we can move ahead with the physical properties. I think up to here it's very clear to you. If you have any doubts, you can put in the comment section, because when I go through it, I'll be able to respond to it in a better way. As of now, there is no comment seen. Yes. Okay, we'll move ahead then. Yeah, here is our next, the properties, physical properties. How are you going to define it? State. Only the first, if you consider the alkanes or the alkenes, the first few members will be gases the same way, because the intermolecular interactions will be very weaker, because of which they exist in the gaseous state. And other carbonyls, the first few up to C10, they are the liquids. Then come after that, the number of carbon atoms increase and they become the solids. Odor. They have the bitter almond-like smell. The lower aldehydes have the unpleasant smell, whereas the higher aldehyde and the ketone, they have the pleasant smell. If you smell the nail polish or the nail polish remover, you can really feel the smell of these. The solubility, the first few aldehydes and ketones, because of the presence of hydrogen bonding. Say, these contain the polar groups. And the carbon chain. Say you have the carbon chain like this, because this is a non-polar chain, whereas this group is polar. This is non-polar. When this non-polar chain is very less, the fewer members, where you have the carbon atoms in the chain, the number of carbon atoms in the chain is less, then the polar groups come into picture, where they can form the hydrogen bond in water, because of which their solubility is more. And then when you go in the next coming compounds, what is going to happen is the carbon chain, the backbone, that increases, the number of carbon atoms increases, and the solubility comes down. So always solubility is inversely proportional to molecular weight. Lower is the molecular weight, lesser with the number of carbon atoms, and that more polar the compound is, because of which it is more soluble. When the number of carbon atoms increase, that the chain length increases, the molecular weight is also going to increase. The extent of hydrogen bonding is less, because the non-polar groups, they dominate over here, because of which the solubility is going to go down in water. Then the boiling point. So boiling point depends. Whenever we say boiling point, it doesn't take into account of the covalent bond which is present in between them, but instead it considers the intermolecular interactions, like the London forces, dispersion forces, or also the hydrogen bond. So if you consider the alcohols can form the greater extent of hydrogen bonding with water compared to the carbonyl compounds and compared to the alkanes, where in case of alkanes, you have only the non-polar chain, where in case of alcohols, you have more extent of hydrogen bonding compared to compared to the carbonyl compounds. So always the boiling point of alcohol is very high compared to comparatively high. If you take the same molar weight, then alcohols have the higher boiling point compared to the carbonyl compounds, compared to the alkanes. Now, the chemical properties we have to study, the reactions of both aldehydes and ketones. So we already know that the bond is very polar, kind of polar, where the oxygen being more electronegative, that drags the electron pairs between carbon and the oxygen. As a result, this gets a positive charge and this gets a negative charge. So due to strong electronegativity on the oxygen, the mobile pi electron, these can be moved to they are pulled strongly towards oxygen, and because of which the carbon becomes deficient of electrons, because of which it can be easily attacked by the nucleophile, which is electron rich. Carbon is the electron deficient center, which can be attacked by electron rich nucleophile. These aldehydes and ketones, they undergo nucleophilic substitution reactions easily. So what are these nucleophilic substitution reactions we have to see? Or nucleophilic addition, I'm sorry, not nucleophilic substitution, this should be nucleophilic addition, because there is a C double bond O. So they undergo, we'll study the nucleophilic addition reactions, how it proceeds. Say HCN, the nucleophile generated is Cn minus. This attacks over here and this bond shifts like this, resulting in the formation of, if you say R, C double bond OH plus HCN, then the Cn minus that attacks over here, this bond shifts over here, resulting in the formation of R, C, O minus, or HCN. And this takes up a proton, resulting in the formation of cyanohydrin. This cyano group, this is hydro group, so this is cyanohydrin. Then If you do the partial hydrolysis of that, what is going to happen? What do you mean by partial hydrolysis? You have the compound like this, RCOH, H, and the mechanism is different, but I'm saying you how to add this H2O, you add to this H2, you add to this, because of which you are going to get RCOH, H, and CONH2. This is nothing but amide, hydroxyamide. If you do the complete hydrolysis, if you're going to hydrolyze it further, then CONH2 groups gets converted into R, COH, H. Always the hydrolysis of this results in the formation of COOH, nothing but hydroxycarboxylic acid or hydroxy acid. Instead, if you are going to treat it with nickel, and so you have this compound RCOH and C triple bond N cyanide, then H. If you are going to reduce it in the presence of nickel, then two hydrogens get added so that the triple bond gets converted to a single bond, and you get RCOH, H, and NH. H2, two hydrogens get added to this, and NH2. This is nothing but amino. This is amino group, and this is the alcohol groups. So starting from the aldehyde or the ketone, if you're going to treat it with the hydrocyanic acid, that's HCN, that results in the formation of cyanohydrin with the intermediate, and on partial hydrolysis it is going to give the amide, hydroxyamide. On complete hydrolysis it is going to give the amino acids or the hydroxy acids, and sorry, not amino acids, it's going to give you the hydroxy acids. And if you are going to treat it with, or if you're going to reduce in the presence of nickel catalyst, then you are going to get the amino alcohols. This is about the nucleophilic addition reaction with HCN. And starting from the same one, if you treat with the, take the formaldehyde, we'll write the reactions of formaldehyde. H, C double bond O, H plus in the presence of Cn minus. This attacks over here, this shifts here, resulting in the formation of H, C, OH, and H and Cn. Now you have different options. Then you do the partial hydrolysis. Then what do you expect? O gets added here, H2 gets added here. As a result, you are going to get H, COH, H, and CONH2. It results in the formation of amide. Then you would do the complete hydrolysis. This is called as glyconamide. Then complete hydrolysis. Then this gets converted to COH, H, then COH. This is called as glycolic acid. Then if you are going to treat it with the nickel in the presence of hydrogen, then HCOH, H, and you are going to get CH2, NH2. So this is ethanol. There are two carbon atoms. So this is ethanol and an amine group. So 2 amino ethanol. If you start this reaction with the acetaldehyde, so all these hydrogens will be replaced by the aldehyde groups, resulting in the formation of lactamide on the lactic acid, which is optically active, which can be optically active, and the aminopropanol. So this will result in the formation of a racemic mixture. Okay, so this is how the reaction of or the nucleophilic addition reactions take place with respect to aldehydes and the ketones. Then we move on to the next step, that's the addition of sodium hydrogen sulfide. So how this reaction proceeds, let me just check if you have any queries over here. Yeah. Okay. Yeah. So what do we have next? I can't go through the link provided. Okay. So yeah. Okay. I'll move ahead. The reaction with ammonia derivatives. I already told what exactly are derivatives. Here, this is addition elimination. Addition happens, then the elimination, which is nothing but the condensation. So the carbonyl group is treated with NH2Z, where it can say NH2, if the Z is equal to hydrogen, then it can be ammonia. Then you are going to get the ammonia derivative. So if the Z is equal to OH, that's nothing but NH2OH hydroxyl amine. If it is NH2 hydrazine, if it is NHC6H5 phenyl hydrazine, this is how all these Z groups are being replaced by different other groups, because of which what you can expect over here is the derivatives. Yeah, so I'll move ahead with this one. Now, what is that you are going to get? How the mechanism proceeds? This has a lone pair of electron, which is going to, yeah, now this comes and attacks over here. This shifts and this takes up a this shifts to oxygen, then it takes up a proton, resulting in the formation of OH and NH2Z. Okay, then this rearrangement takes place and the shifting takes place. There is the OH is going to take the hydrogen from here, resulting in the formation of NHZ. Then it will lose a water molecule, resulting in the formation of a double bond between C and N. And then because of which this gets a positive charge, and to remove this positive charge, a proton will be removed. This is how the reaction is going to happen. So Z is equal to OH, you get hydroxyl amine. So now what is that you are expecting? So here I'm going to write it here, RC double bond OH, and you treat it with hydroxyl amine. This will go here, this will go here, resulting in the formation of RCH and single then you get a double bond N and OH. This is aldoxime. So when the aldehyde is treated with the hydroxyl amine, you get aldoxime. If the aldehyde is treated with hydrazine, you're going to get C double bond N hydrazone. And if you're going to treat it with phenyl hydrazine, you're going to get phenyl hydrazone. And if you're going to treat it with the 2,4 dinitrophenyl hydrazine, which you have done in the laboratory, you are going to get phenyl hydrazone. And then with alcohols and thioalcohols, you can get the acetal, hemiacetal, and the ketone. So these are the products. I'm going to stop it for today. Thank you for watching the video.